Good evening, everyone. Today we will start with Unit 6, that is kinetic methods of analysis. Yesterday we had talked about analysis of data followed by the lab protocols. Today we will be knowing about various kinetic methods and the various process of kinetic analysis. So before going to the methods of analysis, we will first know what do you mean by the kinetics of a reaction, the different types of kinetic methods and how they are calculated, the rate law, the rate equations, and then we will see what is how this kinetic methods or the kinetic reactions they are analyzed. So to begin with, kinetic methods they have been classified according to many classes. So, but in a broader sense, they have been classified in terms of catalytic and non-catalytic methods. Now, the catalytic methods, they have been further divided in terms of the types of the reactions, and the non-catalytic reactions, they have been classified according to their applications on the species. So, there is also another method for classification of kinetic methods, and that is based on the number of the components, like whether it is a single component or multi-component. So when we look into the table 6.1, we see here this is the most generally accepted classification of kinetic models. And from table 6.1, we can see that the kinetic methods, they have been classified into the catalytic methods and non-catalytic methods. In the catalytic methods, we have for the two types of reactions, that is non-enzymatic reactions or enzymatic reactions and electrochemical reactions. In the non-catalytic methods which do not use any catalysis, they have been like they are further they compose they are have been classified into a single component, or they have been used for mixture component. Now here also, so when we look into the different types of classification, there is another classification that has been listed here in table 2. This is classification of experimental approaches that has been based taken for kinetic measurements. This is one is your mixing methods, that is the method based on mixing and following of the reaction, like in terms of batch mixing, stop flow mixing, and continuous flow mixing. We also have relaxation methods, which include the jump techniques, the periodic relaxation techniques, and spectral relaxation techniques like fluorescence and phosphorescence. And there are also equilibrium methods, like the techniques that permit the calculation of rate without disturbing the system at equilibrium, such as the NMR and ESR. So, in a broader sense, we just saw the classification of kinetic methods here in table 6.1 and table 6.2. Now we will come to the calculation of measurement of reaction rates. How can why this reaction rates they are important, and why do we need to calculate the reaction rates? So to begin with, we'll first understand how a chemical reaction is done. So we'll consider a single reactant A which forms the product P. So here this the rate of this equation, that is the disappearance of A and the formation of the product P, here it is shown in figure 6.1. Now when we show from the figure 6.1, in the x-axis we plot the time scale, and in the y-axis we take the concentration. So the rate of the reaction here, it is defined as the rate of disappearance of the reactant A and the rate of the formation of the product P. So by this way, we can actually tell the disappearance of A of the reactant and the formation of the product. So this implies gives us the rate of the reaction. So from both these parameters, either one of these, we can calculate the rate of these reactions. So this rate of this reaction can be measured. So whenever we have by physical methods, we can measure it by conductometry, potential by potentiometry, the pH by using a pH meter. So and in this way we can calculate the rate for simple reactions. Now there are various different methods by which kinetic measurements can be done. So in general, there are two types of ways by which kinetic methods are measured. One is called as the differential method and another is called as the integral method. So now from the name we can understand that in the differential method, concentration of the analytes or the products, they are computed from the reaction rates by means of differential form. So here in differential method, we take the concentration of either the reactant or the product in differential form of rate equation. Now then the rates, we determine the rates by measuring the slope of the curve, and then we find out the rate of the reaction. So but in the integral method, as we know the name implies, the integral method, it is based on the integration of the corresponding rate expressions over the time period. So in general, we see these two methods are mostly employed, that is either the differential method or the integral method. So when we look into this plot, here in plot 6.1, it shows the variation of concentration with respect to time. So this figure 6.1 is the general representation of any kinetic of any rate of a, it is actually a general representation of a chemical reaction, the kinetic measurements. So where particularly in this case we see that are generally applied to the initial portion of this curve. When you look into this curve, that is the disappearance of A or the formation of this product P. So this curve is exponential in nature, that is the kinetic process here is exponential in nature. So the kinetic methods that are generally applied to the initial portion of the curve, that is mostly to the ranging to 1 to 3%, and this portion, such type of kinetic measurements, they are called as initial rate method. So in general, a kinetic reaction, the variation with this plot, we can see, we can find out the concentration of the reactant at a particular time from this curve, and this is how we know the concentration of the unknown at a unknown point. So this is one of the simplest kinetic plot that we come across. Now coming to the calculation of kinetics by the differential methods, so that we just studied, one is the differential method and one is the integral method. So let us understand what is this differential methods. Differential methods, first we should know what is the initial rate method. As the name implies, initial rate method, it is used to determine the concentration of the reactant at the initial phase only, like from 1 to 3%. The solid curves, when we look into here figure 6.2, it shows 6.2a, it shows the plot of data of determination of A by the differential method. Here when we look into figure 6.2a, we can see two types of lines. One is the dotted lines and one are the solid lines. The solid lines, they are the experimental plots that we have obtained, whereas the dashed lines here in figure 6.2a, they represent the respective tangents. So here from figure 6.2a, we see at different time periods we have obtained the different rate of the reactions, that we have obtained different plots. So here when we draw the respective tangents and the slopes of the tangents, then they are plotted against the function of the reactant concentration, as here it is shown in figure 6.2b. Then we can find out from the slope, we can find out the concentration of our reactant. So many unknown concentration, if we don't know, then they are treated in this way, and their concentration, they are known from this graph, and this graph is what is sometimes called as the calibration graph. So the initial rate is, we know that it is linearly related, it is linearly proportional to the concentration, whether the initial portion of the curve is linear or not. So despite this, whether or not the linear portion is the initial portion of the curve is linear or not, but the rate is linearly proportional to the concentration of the reactant. Hence such type of measurements is also called as a single point method. Then this method has certain advantages, like since we only utilize the initial part of the slope, a few data points are taken, and that is why the curve is, it shows a good fit, and the entire procedure is simplified. The reaction, it obeys pseudo order zero kinetics, as the change in the concentration is very small or they can be neglected. Now we can see in this point, as the product formed is very small, the reverse reaction usually does not takes place. The complications is totally can be avoided in this case. The reaction, it takes place faster at the start of the reaction and usually gives us better signals. Now the useful these such types of plots, they're useful for reactions where the rate constants are too small. So then we can use this single point method of determination of rate constant. Now then, one of the shortcoming of this method is lies in the accurate measurement of the initial slope, because the gap is very low. So the accurate measurement of the initial slope is very difficult. So that is the one of the shortcomings of this method. Then coming to fixed time method. So as the name implies, fixed time. So in this case, we keep the delta T constant. That is the concentration of the reaction product. It is measured at determined from the start of the reaction, and since here delta T is constant, the concentration is directly proportional to the change in the concentration of the product. So here, when we see by plotting the product versus the concentration, we see a straight line with zero intercept. Here it is shown in figure 6.3. This is the advantage of using fixed time method, where the delta T here, that is remains constant. Then comes the variable time method. So here, as the name implies, the time is varied. So that is delta P remains constant, and it is measured at different time intervals like T1, T2, T3. Here in figure 6.4, here it is shown the plot of reciprocal of time. Here what the times are varied, but the delta P remains constant, and the plot of this 1 by delta P is taken versus concentration. And then by fixing, the method is limited than the fixed method, because delta T here we plot the reciprocal. However, this is actually a difficult method, because the delta T here, it is we have to take the reciprocal of delta T. Okay. Then comes integration method. So these are the various ways by which differential methods are used. But here we will talk about the integral methods. The experimental procedure here, it is similar to that of the differential methods, but the values are integrated. So first is the tangent method. In the tangent method, the formation of product, it is integrated over a finite time period, that is delta T is equal to T1 minus T2. Product, or log of initial concentration of reactant minus P, here it is, as here it is shown here in y-axis, we plot log P, then it results in a series of straight lines with positive or negative slopes. Here log P is plotted as a function of time. This is the tangent method. In the fixed time method, what we do is we here plot of 1 by delta T versus C0 for a series of standards. They constitute the calibration graph for the variable time method. Then coming to induction period methods. This phenomena, it was observed by Landolt, and between iodide and sulfite, and this is called as Landolt effect. So what happens here is A plus B, they react slowly to form the product P. Now this product P, it reacts with the Landolt reagent in a very fast reaction to give us the final product Y. So the slow reaction, it is linked to the fast reaction through the product P. So here P is the common factor that links these two slow reaction and fast reactions. Now here when we see the time between the appearance of product P, it actually measures the catalyst concentration. The catalyst here is the Landol's catalyst, and it is directly related to the induction period T. So the experimental procedure here, it involves the measurement of time elapsed between the addition of the last reactant, which starts with the slow reaction, and the first appearance of the signal corresponding to the product. This very low concentration of catalyst can also be detected by this method. Then is coming to differential reaction rate methods. Now here table 4, when we look here, in this process, what we do is the various differential rate methods, they have been summarized. Like first is the logarithmic extrapolation method. In this method, when we look into here figure 6.6 and 6.7, it shows the logarithmic extrapolation method for a different types of species. We also have a linear extrapolation method. Here also we have a proportional equation method. Here all the equations have been written. Then next, coming to activation and inhibition. So the rate of any reaction, they can be either increased or decreased by the addition of a catalyst, that we are all aware of. So for the first process after addition of a catalyst lies in the activation or the activation of the substrate. So when the active the with the activation in activation, or when we add a catalyst, they are sometimes called as modifiers. If the equilibrium constant of inhibition reaction is sufficiently large, then the rate is equal to the rate of the uncatalyzed reaction. So here, when we look into the curve, then we can know whether it is an activation reaction or it is a inhibition reaction. Then coming to measurements of partial rate order. So when we see a particular reaction, the measurement determination of the order of the reaction is a very important task. So first we need to find out the kinetic rate equation for the given system, and then we can find out the partial rate order. Now to know the rate equation, we have to depend on the differential method or the integral method. These are the first processes by which we can know the order of the reaction. Then for non-catalytic reactions, we see uncatalyzed reactions. They are like, for example, the selectivity of a complexing agent, they can be controlled by adjusting the pH of the medium. So here the sensitivity can be achieved by the use of spectrophlorometric or spectrophotometric detection to monitor the reagents that form complexon with large molar absorptivities. So here when we have a reaction which are uncatalyzed reactions, we can actually monitor their rate by complexing with some spectroscopically sensitive ions, and then we can find out the rate of their reaction. Then coming to stopped flow technique. So slow reaction kinetics, it is when a closed system is used, so they make use of this stop flow technique. The measurement of fast reactions, they generally require special equipment, but stop flow technique is one of the most popular methods for carrying out rapid reactions, and it is used for the study of reactions with half lives between microseconds and a very few seconds. So here, in principle, the streams of the sample and the reagent, they are mixed very rapidly, and the flow of the mixed solution is stopped suddenly. So as the reaction is mixed very suddenly, the reaction process is monitored slightly downstream from the mixing point. So then this process is further monitored by either a fluorescence or by photometry. Then there are various factors that affect the reaction rate. So one of the some of the common factors that are known to influence the reaction rate are: the first is the temperature, the pH of the medium, the concentration of the reactant, and the ionic strength of the medium. So these are some of the factors which can highly influence the rate of the reaction. So now for this reason, the kinetics of a reactions, they are measured under specified conditions. Like for slow reactions where half lives longer than 2 hours, then the rate can be adjusted so their half life falls within our acceptable range. So we can actually, whenever we talk of the rate of a reaction, we have to always specify the reaction conditions, because the rate of the reaction is highly sensitive to the surrounding parameters. Now coming to mathematical basis of kinetic methods. So first we will know what is the rate law for first order reaction. This is the mathematical rate equation derivation that has been given to you, and you can find out. So first, considering this is equation 1, where it shows the rate equation. Here the rate is given by, when we have a reactant A and it decomposes to form the product B, then the rate of the reaction is given by derivative of A by A, d of A by A is equal to minus K into small change into dt. So ultimately, when we integrate this value within the range and the evaluating, finally we taking the exponential of both the sides, we finally see that the concentration of A at time t by the concentration of A at time 0 is equal to e to the power minus kt. So here we can say, or that concentration of A at any time t is equal to concentration of A at time 0 exponential to the power minus kt. So this relationship here is equation 6.16 is very important, and it shows how can we calculate the concentration of the reactant at any time. So now when we see that, when we want to see what happens, this equation is just for the initial concentration of A. Now we will again consider this equation for the formation of the product P, and finally when substituting the values and for successive periods, we can find out that the final equation here, when we look into this, it can be ultimately given as the product at any time t is equal to a0 into 1 minus exponential to the power minus kt. So this six equation is 6.18. It can be used, or for when we have a time period of t is equal to tau, that is 1 by k, then this equation it becomes 1 by e a0. Or when for a period of t is equal to 2 tau, or this is 2 by k, we have this. So equation 6.20. So likewise we get successive periods for figure 6.8, that here it is shown as this. Similar figure is similar to that of what we call it as the radioactive decay. So this is how we can calculate the concentration of a first order reaction at after any particular time t. One example has been shown. Then coming to rate laws for second order. Now let us consider the reaction in which one or more of reactant A it converts to form the product. So here when we see here A plus R, they react to form the product P. So here the rate law here it can be given as d of a by dt is equal to k into a into r. So what happens here is, then finally putting all the equation with this type of reaction here, it can be given as this. So here table 6.3, where the rate equation, the differential form, the integrated form and the common units for different order of reaction has been shown. Now, also in an example has been shown here how we can calculate the rate constant of this given equation. Here, example 2, 3 has been given for you. Now coming to catalyzed reactions. Now most of the reactions, they are catalyzed by various types of inorganic anions and cations or enzymes. So first we will start with enzyme catalyzed reactions. Now we know enzymes are highly molecular weight molecules. They are used in analytical reagents because they have specific degree of selectivity. That means a particular enzyme will bind to a particular substrate. They will not go to any other substrate. So enzyme catalyzed reactions, they are employed for determination of activators, inhibitors and enzymes itself. Also, they help in determination of various types of substrate. So to understand the kinetics of enzyme catalyzed reaction, we need to consider this equation in equation 6.5. That is, an enzyme, it reacts with a substrate to form the enzyme substrate complex, which then further forms the product and it regenerates the enzyme. So here the different steps along with their rate constants, they have been given here. Now first we will see these are two processes here that are involved. So from these two processes, in the steps that's shown in equation 6.25, we will find out what is the rate of this enzyme catalyzed reaction. So first, in the first case, the rate determined by the rate of complex formation. So the concentration of S and T at any time t, it becomes S minus E0 t, and here substituting all the values of the E and T and finally also applying the steady state approximation, we finally here we get the equation that is called as Michaelis Menten constant. Here it is shown, this is Km, Michaelis Menten constant, and which gives us the final rate equation for enzyme catalyzed reaction. Here it is shown here in figure 6.9, the change in rate of the product formation as a function of substrate concentration. This equation dp by dt is equal to k2 by km into E0 into concentration of substrate at any time t. this is equal to this. Here at this point, the limiting rate of this equation is often referred to as nu max, and when the substrate concentration at exactly nu max by 2, it is equal to km. So this is how we derive the function for enzyme catalyzed reaction. And equate here in example 3, an example has been given to calculate the rate of the reaction of an enzyme catalyzed reaction. Just by simply putting the formula, we can find out the rate that is required. Now there is comparison of graphical logarithmic extrapolation methods and method of proportional equations. So graphical logarithmic extrapolation, the advantages are that they are useful for the determination of mixtures without separation. No prior knowledge of rate constants are required. They are less prone to error because the linear plot is based on several concentrations. They can be used for the determination of three components in a mixture provided that they have different rate constants. The selective determination is quite simple, and it can be done easily with the help of spectrophotometry or spectrofluorimetry, and temperature is not a crucial variable here. But however, there are certain disadvantages of this graphical logarithmic extrapolation, like the rate constants, they must differ considerably for the mixed components. Then total concentration of the species, it must be known. The faster reacting component must be reacted to almost 99%. A large number of samples need to be drawn for analysis because continuous monitoring is not possible in this case, and the procedure is very laborious and time consuming because it requires constant monitoring and making plots. So hence this process is usually, it has more disadvantages than advantages. Then coming to method of proportional equations, the advantages are that they are very much ideal for fast equations and initial rate methods. They require shorter time than the graphical methods. The prior knowledge of total concentrations are not required. They can be applied to mixtures that involve complex kinetics. The difference in the rate constants, as small as value of 4, is sufficient to cap for multi-component analysis, and they can be easily adaptable for automation for the determination of more than two components in a mixture. Then they are also associated with certain disadvantages, like prior knowledge of the rate constants are definitely required here. They are not applicable to systems that involve synergism, and though theoretically, no, they have no limit, but that is not possible to extend beyond four components. So these are the some of the disadvantages that we encounter with method of proportional equations. Now coming to instrumentation. Kinetic methods, like, they do not require measurement of absolute values, but rather they measure as a function of time. So here the components for measurement of kinetic measurements are: first is mixing of sample and reagent and carrying out the reaction in a vessel under thermostated condition. This is important. Then measurement of the concentration changes or any other change in a parameter as a function of time. And third is data collection and processing. Now strict control of temperature is always an important parameter because the reactions are carried out under thermostated conditions. Here in figure 6.10, a schematic diagram of a stopped flow technique, here it is shown. The kinetic reactions can be monitored in either in a closed vessel or in an open vessel. In a closed vessel, the mixing operation is usually done manually or automatically, and it is used for slow reactions. However, for open systems, they are commonly used for the study of very fast reaction kinetics and with the help of batch systems. The various parameters that has been presented in table 6.2. Then in the flow method, after mixing, the required parameter is measured at a point where the steady state is achieved. The flow methods, it comprise of continuous flow, accelerated flow, segmented flow, pulsed flow, and stopped flow. Then other techniques of fast reaction studies that include a direct relaxation method such as temperature jump, pressure jump, electric field jump, pH jump, and periodic relaxation methods and pulse methods such as flash photolysis or radiolysis. Then comes the detector. The detector usually comprises of optical methods such as UV visible spectrometry, fluorescence, NMR, ESR. The detector also includes electrochemical methods like potentiometry, conductometry, polarography or amperometry, and also radiochemical methods and thermometric methods. So by this is how a kinetic measurement setup is done. Then coming to applications of kinetic measurements. The important areas of applications of kinetic methods are mostly in environmental chemistry, clinical and pharmaceutical chemistry, sometimes in industrial products such as aluminium or petroleum derivatives, also in geochemistry, agricultural chemistry, food analysis, and analytical grade reagents. There are three ways of testing the performance of a kinetic method. That is, first is application to real samples, application to spiked real samples, and application to simulated, or the, what we call it as synthetic samples. Now, real samples are actually, they are the analyte of interest. The result has to be compared with an acceptable non-kinetic technique. Thus, the kinetic determination of metal ions, they are compared by AAS, that is atomic absorption spectrometry, visible spectrometry, or NAA, that is neutron activation analysis. Now, when we have an analyte that is too low, or the known concentration that is present in very low concentration in the sample, then we spike it. It is spiked, and then it is compared to the result of a stand that is was obtained in a standard kinetic method. So a recovery of 95 to 105%, they are generally acceptable. Then coming to simulated or synthetic samples that are employed in the analysis of wastewaters, seawaters, and nuclear fuels. These should match faithfully the real counterparts, that is both in analyte content and treatment. The real and simulated samples, they are more commonly used for evaluating the efficiency of kinetic methods. Kinetic methods that are used for the determination of both organic and inorganic species, they fall into two categories, that is the catalyzed and uncatalyzed reactions. The catalyzed reactions are more selective and sensitive and most commonly used than the uncatalyzed reactions. However, the uncatalyzed reactions are quite useful when high speed automated measurements are required or when the sensitivity of the detection method is great. Now, various metals like manganese, iron, copper, vanadium, carbon, bismuth, nickel, chromium, mercury, molybdenum, ions like sulfide, phosphate, and cyanide are the most commonly and frequently assayed in real samples by different kinetic methods. So, this is the application of different kinetic methods. So, here some of the questions have been given for self practice along with their answers, and you can go through it. So with this, we end unit 6 and we'll start unit 7, that is acid base equilibria. We'll take a short break of 5 minutes and then we will start this. So now we'll start with acid base equilibria. So here in this section, we'll talk about the concept of acids and bases, the different concepts of acids and bases, and the buffers, pH, and so on. So first we'll begin with the concept of acid and base. So there have been several theories that have been proposed to explain what is an acid and what is an base. There are three common accepted theories. One is the Arrhenius theory, the Bronsted-Lowry concept, and the Lewis concept. So Arrhenius is the old one and it has been widely accepted. So according to Arrhenius, an acid is a substance which dissociates partially or completely to yield hydrogen ions. And base is a substance which dissociates to give us hydroxyl ions in aqueous solutions. Like for example, HCl is an acid because it dissociates to give H plus ions in solution. Whereas according to Arrhenius, NaOH is a base because it gives us OH minus ion upon dissociation in aqueous solution. So here, by definition, if we look into the three examples, by definition, HCl and CH3COH are acids, whereas NaOH is a base in nature. But the Arrhenius theory, it fails to explain certain situations. Like for example, here Debye and Huckel, they clarified that the proton exists in aqueous solution in close association with water molecules. Like according to Debye and Huckel, HCl, the dissociation of HCl should be shown as HCl plus H2O gives rise to hydronium ion plus Cl minus. So here, so when we apply Arrhenius theory to this equation, then we see that HCl is not an acid because no H plus ion is present. So thus Arrhenius theory, it fails here. Again, when we look into HCl plus NH4 NH3, it gives NH4 plus, so Cl minus. Here no OH minus ions is present. So here, as also as per Arrhenius theory, ammonia is not a base. Therefore, the failure in these two examples of, they suggested that Arrhenius theory has some limitations and new theories were proposed. Now, the second theory that was proposed in relation to definition of acids and base is the Bronsted-Lowry theory. So here this theory was proposed by two scientists, Bronsted and Lowry, and they proposed it individually. However, here they state that an acid is a substance which can donate a proton and base is a substance that can accept a proton. For a molecule to behave as an acid, it must encounter a proton acceptor. So according to this concept, the product formed when an acid gives up a proton is a potential proton acceptor, and it is called as the conjugate base of the parent acid. So when, let us see the following example. Here acid 1, it gives up a proton to form the base 1. So that is why acid 1 and base 1, here acid 1 and base 1, they are conjugate acid base pair. Similarly, when we have a base, it produces a conjugate acid by accepting a proton. That is, base 2, it accepts a proton to form the acid 2. So here base 2 and acid 2, they are conjugate acid base pair. Now when we combine this equation, we can write that acid 1 plus base 2 gives rise to base 1 plus acid 2. So this is what is a conjugate acid base pair reaction. The extent to which this reaction proceeds, it depends on the relative tendencies of the two bases to accept a proton or two acids to donate a proton. Now when we look into, for the example, given example, the in aqueous solution of acetic acid, water accepts a proton and therefore it acts as a base with respect to the solute. That is, here as acetic acid plus water, it gives rise to H3O plus acetate ion. That is, the conjugate base of acetic acid is the acetate ion, and the conjugate acid of water is the hydronium ion. So this is how we identify a conjugate acid base pair. Then coming to the Lewis theory. Here Lewis introduced the electronic basis of classification of acids and bases. So according to this theory, an acid is a substance which can accept an electron pair and the base is a substance that can donate an electron pair. So the various examples, some of the examples has been shown here, like in example 1, BCl3 plus NH3, it gives rise to this product. So here NH3 is the Lewis base because it can donate an electron pair, that is the lone, that is the electron that is present over N. But here the BCl3, it is the Lewis acid because it can accept the electron pair from NH3. So this is how classification of acids and bases has been done according to three classifications. Then coming to autoprotolysis and labeling effect. Now solvents have been generally divided into three classes based on their proton donor accepting properties. Now a solvent may be amphiprotic, aprotic and basic but not acidic. So amphiprotic solvents are those which show both acidic and basic properties and they undergo self dissociation or autoprotolysis. That is, one molecule it acts as acid, whereas the second molecule it acts as a base. This is what we call as a autoprotolysis. Water is the most common example of this class. So we can, how water is an example of a autoprotolysis, here it is shown here in the, in these equations. Here in first equation, H2O, it forms H3O plus OH minus. Methanol and ethanol also show acid base properties similar to that of water. So these are some of the examples of autoprotolysis. Now depending upon the acidic and basic properties, a solvent may also show a leveling effect upon the solutes and bases. So if we have a solute acid Hb, which is a strong proton donor than the solvated proton, then the position of the equilibrium in the reaction, it becomes this. We have a solute acid Hb, then the solvent here, it is the proton, then it becomes shb plus sh plus b minus, that is the equilibrium will be towards the right. Where if we say the hb is very much stronger than sh plus, then the equilibrium will lie far to the right and hb will be dissociated. So this is how acidic, suppose we take the example, a series of different acids, they can be, when we have a series of different acids which are very much stronger than the solvated proton, then they will dissociate completely, and the such solutions will be brought to a level of acidity that is governed by the acid strength of Hs. This is known as your leveling effect. Now we have like acids such as perchlorate, HClO4, HCl and HNO3. These are the strong proton donors than H3O plus. So therefore all these acids are leveled to the strength of H3O plus. This is called as leveling effect. Then coming to monoprotic acids and monoacidic bases. So the difference between a strong electrolyte and a weak electrolyte is that a strong electrolyte undergoes complete dissociation, whereas a weak electrolyte, it undergoes partial dissociation. So therefore, in the case of strong electrolytes, the concentration of associated ion can be determined directly from the molar concentration of the electrolyte. That is, when we have a zero point 0.1 molar of HCl, it gives 0.1 molar of H3O plus, and 0.1 molar of NaOH will always give 0.1 molar of OH minus. However, in weak cases, the concentration is not directly identical or to the molar concentration of the acid or base that have been taken. Then coming to ionization equilibria for weak monoprotic acid. Suppose here we have a weak acid HJ, which on dissociation forms H3O plus A minus, and then the acid dissociation, water dissociation, all have been calculated, and finally it gives a cubic equation of this step. Here equation 7.6, which is an exact equation. It gives the hydronium ion concentration of a monoprotic acid. Simpler forms of 7, this equation has been used. Now what happens here is, when we, so to simplify this equation 7.6, we will have the first assumption. So when the concentration of OH is very small, that is most less than 5% of H3O plus, then what happens here is H3O plus minus OH minus, the concentration becomes almost equal, and then here the equation 7.6 is changes to this. Then we will have a second equation assumption where the HCO, the amount HCO is very less than 5%, and then we get this. So upon simplification of equation 7.6, we can calculate the this for calculating the concentration of a weak acid. Then coming to ionization equilibria for weak monoacidic bases. So monoacidic bases, similarly, we can use the different the equations here, the dissociations, and here this also yields a cubic equation here, sub here, and we can find out as we'll take certain assumptions where the in the first assumption we can see that the concentration of H3O plus is less than 5% the concentration of OH minus. This simplifies to OH minus, the concentration of OH minus being this. Whenever we'll again go for an assumption, if OH minus concentration is less than 5% of this, we can use this equation to calculate the OH minus concentration. So here two equations have been given and you can calculate just by simply by putting the above formula. Then coming to polyprotic acids. Polyprotic acids are those which dissociate in solution in batches or in different steps, and they are able to donate more than one proton per molecule to the acid. Like H2SO4 is one common example of a diprotic acid. Even H2CO3, that is carbonic acid, is also an example of this. Triprotic acid is phosphoric acid H3PO4. So there are successive steps of the dissociation by the hydronium ions, and you can see. So solutions which contain a diprotic acids, we can write them as H2A because they can donate 2H plus ions. So here these are the equations that describe the dissociation of H2A molecule. Then we apply the general procedure for the determination of the H3O plus ion for a diprotic acid. The These are the certain steps they are applied, and finally if the person will consider, the first assumption is that the concentration of H3O plus is calculated using this formula H3 root over of Ka1 Kca. Then the value of H3O plus that is obtained in step 1, it is used to determine the percentage of Ka and the percentage of H3O plus. Then we'll put the formula and we'll take the subsequent cases to finally obtain the concentration of hydronium ion. Now let us consider when the solutions contain a polyprotic acid. Now there are several molecules that has two or more acidic functional groups. So in such cases, when two or more functional groups they are present, what happens in such cases? The successive acid dissociation constants they are generated. Now, so what happens in this case? We only consider the first two dissociation points. They are because they are important. Rather, the others can be neglected, and this has been demonstrated here in this following equation example. So here it is given that calculate the hydronium ion concentration of 1 into 10 to the power 3 molar solution of phosphoric acid, and the successive dissociation constant, that is K1, K2 and K3 for three different steps has been shown here. So it has been asked to find the concentration of hydronium ion. So therefore using the above formula we can find out. Then coming to solutions which contain a polyacidic base. So in case of polyprotic acids, only two dissociation equilibria were considered. However, in similar manner will be developed for diacidic base. So diacidic base means it has two OH minus ions. So like similarly, the concentration of OH minus can be calculated using this formula, and then they have been simplified. Here an example has been given. Now coming to buffer solutions. So what are buffer solutions? A buffer solution is one which resists change in pH upon addition of small amount of an acid or a base upon dilution. So such type of solutions they are called as buffer solutions. Now in general, a buffer solution contains a weak acid and the anion of the weak acid, or a weak base and the cation of the weak base, that is the conjugate acid base pair, such as acetic acid, acetate ion, ammonia, NH4 plus. Such type of conjugate acid base pairs they usually form buffer solutions. Now for a buffer solution, how can we calculate the pH of a buffer solution? Let us consider a solution which consider a weak acid and its conjugate base may be acidic, neutral or basic depending upon the competitive equilibrium. So for this equation, Ha plus H2O forming H3O plus A minus Kb has been found to be this. This solution is acidic when the equilibrium first equilibrium is more favorable than the second, and it is basic when the second equilibrium lies far right to the left. When the second equilibrium lies farther to the right than the first. So here the equation has been given, and simplifying all the equations, we can find out the pH can be written as pKa plus log of concentration of Cb by Ca. So here the various properties of buffer solutions have been discussed, like if what happens to the effect of added acids and bases. In general, we know that buffer solution, they consist of conjugate acid base pairs. Now, such as we have acetic acid, acetate, etc. These components, they react with the H plus and OH minus ions that are added externally to the solution. So when we have a Ha and A minus buffer, if we add a small amount of OH minus, this OH minus can react with Ha to form A minus and H2O plus. Or if a small amount of HCl is added, then the H plus is consumed by A minus. So therefore, the acid or base added is neutralized, the sole effect being a small change in the ratio of Ha by A minus, and therefore in such cases the pH does not change appreciably. To change the pH by 1 unit, it is required that we change the concentration of the acid base pair by a factor of 10. So in general, when we add any acid or base to in small amount to an buffer, the pH does not change appreciably. Then looking to the effect of dilution on the pH of buffer solution. So the pH of a buffer solution, it remains constant on dilution. Let us consider a solution of 0.2 molar ammonia and zero point 0.3 molar ammonium chloride, which has and the pH of this buffer is 9.07. If enough water was added to 100 ml of ammonium chloride mixture to make exactly 1 liter of solution, then the pH of the tenfold more solution would be 9.05, big 7, because the mixture of the conjugate acid pair, the ratio, it determines the pH. So it has to be, we need to know that a tenfold dilution, it results just in a pH change of 1 unit. So when 0.01 molar NaOH, whose pH is at 12, that becomes pH 11. This limits the usefulness of strong acids and bases as buffers. That is why dilution has no effect on the no effect on the pH of a buffer. Now coming to buffer capacity. So the buffer capacity of a solution, it is defined as the number of moles of a strong acid or base which is required to change the pH of 1 liter of a solution by 1 unit. Since the buffer capacity is defined as beta, it varies with composition. It is actually represented as beta is equal to D of Cb by dpH, or is equal to minus of D of Ca by dpH, where dCb and dCa represents the number of moles. Cb represent the number of moles of strong base, and C8 represents the number of moles of strong acid that is required to bring about the change in the pH. So the capacity of a buffer solution, it not only depends on the concentration of the two components but also on their concentration ratio. Buffer capacity, it decreases fairly rapidly as the concentration ratio of acid to conjugate base becomes larger or smaller than unity. The maximum buffer capacity occurs when the concentration of acid and conjugate base are equal. So here the buffer capacity, the change in buffer capacity as a function of logarithm of the ratio CNAA by B, here it is shown here in figure 7.1. So here in this chapter, since it involves a lot of numericals, you can go through these numericals and the assessment where the answers have been done. So you can find out the numericals on the how to identify conjugate base and conjugate pair, and the calculation of the pH and pOH of the buffer solution and acetic acid. So here with this, we finished unit 7. We'll start unit 8 just in a few minutes time. So now we'll start with the next unit, that is neutralization titration. So here in this unit we will be discussing the different titrimetric analysis. So the determination of equivalence point, titration curves, the different types of titration curve, indicators, the theory of indicators, and how they are used in neutralization reactions. So first is the basic concept of titrimetry and the primary and secondary standards. So whenever an acid base titration is involved, a neutralization reaction is followed because the acid reacts with an equivalent amount of the base and a neutralization reaction occurs. So the point at which this neutralization point is reached, it is called as the equivalence point, or what we call it as the end point of this solution, and we see a subsequent change in the solution. So for any actual titration, the correct endpoint will be characterized by a definite value of the hydrogen ion concentration of the solution, and which is also dependent upon the nature of the acid and base of the concentration of the solution. So now coming to definition of a primary standard. So primary standard is a substance which satisfy the following requirements. That is, it is easy to obtain, it should remain unaltered during the process, it should be capable of being tested for impurities, like it should be free from impurities and other sensitivity, it should have a high equivalence so that weighing errors are negligible, it should be readily soluble under experimental conditions, and the reaction with the standard solution should be stoichiometrically and practically instantaneous. Now, however, in practice, it is actually difficult to obtain a primary standard, and therefore certain compromises have been made. So generally, we employ sodium carbonate, sodium tetraborate, potassium hydrogen iodide, benzoic acid as primary standards. The secondary standard is a substance which fulfills the requirement that it can be weighed accurately to provide a known amount of the reactant, but it is not a pure substance. So it is used for standardizations and whose content of the active substance has been found by comparison against a primary standard. Then coming to titration curves. So a titration curve is plotted by plotting the pH of the solution during the titration versus the amount of acid or base. So these curves, they are useful to identify the equivalence point graphically. Although while performing the experiment, we can visualize the the equivalence point, but from the titration curves, we can graphically know the equivalence point. The change in pH is of great importance, so because it enables us to select an indicator, that is why selection or choosing an indicator for a titration process is very important. So now let us talk about the titration of a strong acid versus a strong base, that is HCl and NaOH. So here so here the H plus and OH minus ions, they combine to form H2O, whereas in the solution the Na plus and Cl minus, they remain as such. So that is why the solution, the pH of this solution is remain neutral. So the calculation of the titration curves, it involves the computation of the pH for the concentration of the particular species at the various stages of the titration. The pH during neutralization processes will be calculated as follows. First, up to the equivalence point, the pH of the solution is determined by the amount of the strong acid that is present. At the equivalence point, the pH is 7. After passing the equivalent point, the pH is defined by excess of the base. So here, figure 8.1, we can see the neutralization curve of 100 ml of HCl with NaOH of same concentration. You can see how it is graphically represented. So then in table 8.1, we can, here it has been listed the pH during titration, what happens when NaOH is added to 1 ml of solution, and what happens to the pH of the solution. So here in figure 8.2, the neutralization of 100 ml of HCl with NaOH of same concentration with different concentrators indicators have been used and it has been indicated here. Then coming to titration of weak acid versus strong base. So here in this case we will consider a weak acid, that is acetic acid, and again we will consider a strong base, that is NaOH. So here the CH3COH, it dissociates to form CH3COO minus and H plus, and the NaOH, it dissociates to form Na plus and OH minus. But the weak acetic acid is a weak acid. That is why a very few amount is only ionized and it is neutralized to water, and an equivalent amount of the salt, that is sodium acetate, remains in the solution. Now when we start the titration of this solution, we have zero point 0.1 molar acetic acid. So as the titration begins, some of the acetic acid is converted to sodium acetate and a buffer is set up. But as the time proceeds, the pH increases slowly because the ratio of the acetate ion to the acetic acid, it changes. Whereas at the midpoint of the titration, the acetate ion and the acetic acid concentration, they are equal and the pH is equal to pKa. So at this point we have only the solution of sodium acetate. Since this is a Bronsted base, the pH at the equivalence point will be alkaline, and then the pH will be dependent on the concentration of sodium acetate. So the higher is the concentration of sodium acetate, then higher is the pH. So therefore here is how the pH titration curve of looks of acetic acid versus sodium hydroxide looks like. So the slow rising point here is this before the equivalence point, it is called as the this region, it is called as the buffer region. It is flattest at the midpoint and the buffer capacity is greatest at a pH corresponding to pK. The buffering capacity is also dependent on the concentration of the acetate ion and the acetic acid. So from plotting the titration curve, the pH can be calculated using this formula. pH is, this is Henderson-Hasselbalch equation and it can be calculated from this. So, and the table 2, you can find out the neutralization of 100 ml of 0.1 molar acetic acid and 100 ml of zero point 0.1 molar any acid with sodium hydroxide. In figure 8.4, you can see the titration curve for 50 ml of 0.1 molar phosphoric acid with 0.1 molar KOH. This is how we have two different points, because here the first point corresponds to KH2PO4, the second it corresponds to K2H2PO4. Then coming to the titration of a weak base versus strong acid. So the titration of a weak base with a strong acid, it is similar to the above case, but the titration curves are reversed. This neutralization reaction can be illustrated by the titration curve of 100 ml of 0.1 molar, we will take ammonia. This is a weak base, and 1 molar of acetic HCl, that is a strong acid. So NH3 plus H plus Cl minus, it forms ammonium plus Cl minus. Here in figure 8.5, the pH titration curve for 100 ml of zero point 0.1 molar ammonia with 0.1 molar HCl, here it is shown, and the equivalence point is around this. So when the reaction at the beginning, we have 0.1 molar ammonia as such, and the pH is calculated for a weak base because ammonium hydroxide is a weak base. Now as soon as some acid is added, some of the ammonia, it gets converted to NH4 plus, and then a buffer region is created. The endpoint is judged by here the inflection point of the titration curve, but the jump in pH is smaller, that because that is here we see a small jump in pH, and then we can calculate the pH using up to the equivalence point using this equation. So here one example has been shown how to calculate the pH of the equivalence point. Then coming to the fourth case for the titration of weak acid versus weak base. So in this case, we will consider a weak acid, that is 0.1 molar of acetic acid, and a weak base, that is 0.1 molar of ammonia. So the pH at the equivalence point is given as half pH is equal to half pKw plus half pKa minus half pKb. So here comes to be 7. The neutralization curve of the equivalence point here, it is almost identical. When we look into figure 8.5, it is almost identical with that using sodium hydroxide as the base. But beyond this point, the titration is virtually the addition of zero point 0.1 molar ammonia solution to ammonium acetate. And here equation 8.5 is applicable. So the main feature of the curve is that the change of pH near equivalence point and during the whole of the neutralization curve is very gradual. We can see it is very gradual and not very fast. Here in figure 8.6, here it has been shown. So in this sort of titration, there is no sudden change in pH, there is no sharp end point, and this can be found with a simple, no sharp point can be found. So here a mixed indicator is which exhibits a sharp color is mostly suitable. Thus, for acetic acid and ammonia salt titrations, neutral red methylene blue indicator may be used on the whole, but it is best to avoid the use of indicators involving both weak acid, weak base. So then coming to titration of sodium carbonate versus strong acid. Sodium carbonate is a Bronsted base that is a primary standard for standardization of strong acids. It hydrolyzes in two steps. First, carbonate plus H2O giving rise to bicarbonate ion plus hydroxide ion. Then bicarbonate ion plus H2O giving rise to CO2 plus H2O plus O minus. The subsequent steps have been given there. HCO3 minus is the conjugate acid of carbonate ion, and H2CO3 is the conjugate acid of HCO3 minus ion. So here the titration curve for Na2CO3 and HCl, here it is shown in figure 8.7. This is that is the in the solid line. So even though the Kb1 is considerably larger than the 10 to the power minus 6 here, that is the required point, the pH break here is decreased by the formation of CO2 beyond the first equivalence point. So the second point here, it is very sharp. The second endpoint is comparatively sharp than the first one, but this endpoint has been sharpened because the CO2 produced from the neutralization of H3O minus is volatile and it is boiled out of the solution. So what happens here is, in this case, at the start of the titration, the pH is determined by the hydrolysis of carbonate ion. After the titration is begun, the part of the CO3 2 minus is converted to bicarbonate and a buffer has been established. At the first equivalence points, there remains a solution of bicarbonate. Beyond the first equivalence, the bicarbonate is converted to carbon dioxide and a partial buffer region is established. Thus, the pH at the second equivalence point is determined by the concentration of carbon dioxide. Now, in this case, to determine the first equivalence point, phenolphthalein is used, whereas to determine the second equivalence point, methyl orange is used. Neither the point, however, is very sharp. In actual practice, the phenolphthalein endpoint is only to get an approximation where the second endpoint will occur. So the second equivalent point is very accurate, and that is why methyl orange it has been used. Then coming to titration of polyprotic acid versus strong base. So diprotic acids, they can be also titrated stepwise if they behave like a mixture of two acids. So when we have sulfurous acids, we have also Ka1 and Ka2. So that is, it is evident there will be sharp change of pH near the first equivalence state, but for the second stage, the change will be less pronounced. Even for carbonic acid, there will be to Ka1 and Ka2. Now, when we plot the titration curve of a diprotic acid versus sodium carbonate, so during the titration up to the first equivalent point, a solution of Ha minus upon acid, a buffer is established. So here at the first equivalence point, Ha minus exists as this, and beyond this point, after second equivalent point, the pH is determined from the hydrolysis of A2 minus. So for a triprotic acid, these steps they determine the exact equivalence points. So the overall ionization constant is the product of the individual ionization constants here in this case, and it is represented in equation 8.13. Now for orthophosphoric acid, it behaves as a mixture of three monoprotic acids. So the pH for the first equivalence point will be given like this. the second equivalent point is this, and the third equivalent point is this. So then finally the experimental will be the given calculated to be this. So this is how we calculate the pH of different type from different titration curves. Now coming to indicators. So we know that indicators are the organic substances which indicate a change in chemical reaction due to the change in color. Their indicators are of various types. They might be acid base indicators, redox indicators, they might be adsorption indicators. Now acid base indicators, they are the organic substances which have one color in acid medium and a different color in alkaline medium. So the following theories they have been put forward. Like first is the mostly common accepted theory is the Ostwald's theory. So according to theories, weak acids or bases HIN or INOH whose colors are different from that of the indicator ion formed by their dissociation. So when we look into the dissociation of HIN, that is H plus IN minus, or INOH, this is OH minus plus IN plus. So if the indicator is a free amine or a substituted amine, then the equilibrium might be written as IN plus H2O forming OH minus plus HIN plus, and they can be dissociated in aqueous solution as this. So now when we apply the law of mass action, Ka is given to be this, from where we find H plus as this in equation 8.18. So now when we rewrite equation 8.18, we can find out that pH is equal to log of In minus upon In plus pKa. So in this equation, H, the concentration of the indicator represents the concentration of the undissociated indicator whose color is called as acid color, while In minus, it denotes the concentration of the indicator anions, that is the color of which it is present in the alkaline medium. So Ka is the dissociation constant of the indicator acid. Now the indicator base may also be characterized similarly that we have done for indicator acid. Like here we can write pH, the pH can be written as pKw minus pKb plus log of INOH into IN plus, where Kw represents the ionic product of water, Kb denotes the dissociation constant of the indicator base, that is which is the color of the in alkaline medium, and the acid color is due to IN plus. Then coming to the modern quinoid theory of indicators. So according to the modern quinoid theory, an acid base indicator, it is a dynamic equilibrium mixture of two alternative tautomeric forms. One is from the benzoid while other is the quinoid. So out of these, one form it exists in the acidic solution while the other it exists in the alkaline solution. The change in pH it causes the transition of benzoid form to quinoid form and vice versa, and consequently a change in color is observed. So these color changes in case of methyl orange and phenolphthalein, that is due to benzoid and quinoid theory, is given below. So here for methyl orange, this is the structure of yellow benzoid form in bases, but this is the structure of the red quinoid form in acid. This is for methyl orange. Similarly, for phenolphthalein, this structure relates to its colorless nature in acidic form, and this that is in benzoid form, and this is the pink, deep pink form of quinoid form of phenolphthalein in alkali. So this is how the modern quinoid theory it explains the color of indicators. Now coming to the color range of an indicator. A large number of acid-base indicators are available which possess different color according to the hydrogen ion concentration in the solution. So the important characteristics of this color is that the change from a predominantly acid color to a predominantly alkaline color, it does not occur suddenly, but it changes gradually, and it is termed as the color change indicate interval of the indicator. So in this pH interval, the indicator shows mixed colors of different shades of the acids and alkaline colors. The color intensity of one color indicators, it increases gradually. The acidic red color of methyl orange and methyl red is more sensitively perceivable besides the alkaline yellow color, since the color is more, since the color intensity of red is greater. So here table 8.3, it summarizes a selected list of indicators that are suitable for neutralization reactions. So here when we have brilliant crescile blue in acid, they are 0 to 1. In acid solution is red orange, the color is blue in alkaline solution. Suppose we have methyl orange. The pH range is 3 to 4.4. In acid solution, it is red. In alkaline solution, it is orange. So here, some of the transition ranges and color of certain indicators have been shown. Then comes the selection of indicator and what is an indicator error. The primary consideration in choosing an indicator for a given titration is that the indicator should change, that is at the end point should occur within the required increment delta nu of the equivalence point. As a general rule, it may be stated that for a titration to be feasible, there should be change of approximately 2 units of pH or at a stoichiometric point that is produced by the addition of the reagent. So the pH range at the either side of the equivalence point is calculated, and the difference will indicate whether the change is large enough to permit a sharp endpoint. So alternatively, the pH change on both sides of the equivalence point is noted from the neutralization curve determined by potentiometric titration. So here, if the pH change is satisfactory, an indicator should be selected that changes its color or at the near equivalence point. Next, the molar absorptivity of the indicator in needs two forms. It should be known in order that the amount of indicator required to give a readily observable change can be determined. The personal preference to the operator can be consulted as a selection of colors. Okay, so here it should be added that indicator reaction should be fast. Then coming to indicator error. The indicator error follows from the fact that the indicator itself will consume a certain amount of the standard solution. The amount of this solution of the standard solution, it depends upon the nature of the indicator and its concentration, whether it is like alkali or for instance etc. If CT is nu T is greater than C indicator nu indicator, then nu T and nu indicator are the volumes of the titrant and indicator respectively. So the indicator error will be very negligible. So here in this unit, we have talked about titrimetry, the different types of titration curves of different types of acid-base neutralization curves, the method of calculation of pH of different titrimetric titrations. So here some of the terminal questions have been provided along with the answers have been listed here. So after solving this will be useful on your part to go through this chapter. So with this, we finished the unit on neutralization reactions, and the other unit, that is unit 8. So in next class we'll start with the next sections. So this much for today. Thank you all.
Thank you, ma'am.
Thank you, ma'am.